In this video, we're going to be looking at finding volume of solids with known cross section. So this is the other type of solid that we're going to engage with this year in AP Calculus and learn how to find the volume. In this case, by summing up prisms. Summing up prisms. So let's look at an example. If you'll jump down in your notes actually and look at example 1, we've got a base of our solid that's bounded by y equals x squared and y equals the square root of x. And that's the graph that you can see here on the screen. I want us to take a moment to kind of try to visualize what's happening here before we learn how to find these volumes. So you can see here on the left, we've got x squared, square root of x. It bounds this region here. And what we're going to do is we're going to have shapes coming up out of the graph. You can see here there's one little line drawn here. This might be kind of like the representative rectangle that we've been drawing in. And we're going to have different shapes come up out of the page. Over here on the right, you can see the graph has been kind of rotated, and you're going to be able to see these shapes and what it looks like. So we're going to start with a square. I'm going to put a square in there. And if I drag it across, let me drag it back. You can see like when we start there at 0, the squares are going to be really small because the distance between the two graphs is really short. But as we move across the solid, you can see that the distance between the graphs gets larger, and therefore the squares get larger. And then as we get closer and closer to 1, the squares, of course, are going to grow smaller. Again, because that distance between the two graphs is getting smaller. Now this example here, I've only got 13 squares showing, but of course the idea is that we want that number of square prisms. Imagine that these are like solid and filled in between the squares. We want that number of prisms to approach infinity. And so if I raise the number there, you can see how that solid fills in, and imagine a little bit of what that solid would look like. Now it's still a little bit kind of chunky, you might say, because we've only got 100 prisms showing here. We would want that to make its way towards 1,000. Now these shapes, they are perpendicular to the x-axis, and so the height of our prisms, which would be the distance between the squares that's showing here, the heights would still be that delta x, which we saw with our rectangles in area. The height was delta x when we were doing cylinders in the solids of revolution, and now our height is the delta x for these prisms that have squares as their base. So I'm going to, let's just look at how to find the volume of this prism first, and then we'll talk about the different shapes. So if you remember from geometry, the volume of a prism is big B times H is probably how you learned that formula. And big B is the area of, in this case, a cross-section perpendicular to the x-axis. You learned it as area of the base. What I'm going to do is when we take that delta x down to 0, as the number of prisms goes to infinity, delta x goes down to 0. Our integral, we're going to integrate, instead of putting big B, I'm going to have us learn this as area of the shape. Instead of area of the base, I want us to do area of the shape, and I think you'll see why in just a moment. Of course, times dx for the height from x1 to x2 or from a to b. Just using x's here to remind us those should be x numbers whenever we have a dx over here. So let's look at our first example here, the one we were just looking at on the GeoGebra. If I draw in my representative rectangle in the region, I always want to start by doing that. And imagine there are squares coming up out of your paper. So this rectangle, which we've drawn in here, is going to be one side of those squares. If we think about a square, the area of a square is, of course, side squared. And so this rectangle is that side, and it's going to be equal to, again, just like we've been doing the whole time, top minus bottom. Our side is going to be top minus bottom, which in this case is the square root of x minus x squared. And so once we have that, then we're able to plug into our formula. This is going to be the integral of the area of the shape. My shape is a square, area is side squared. And so I'm going to do square root of x minus x squared squared dx, side squared times the height of the prism, which is our dx. I need limits on the integral. We're starting at 0, and we're going to 1. And for us today, let's just focus on setting up the integral. This is an integral that we could evaluate on our calculator if you had a calculator. But for now, let's just get the integral set up correctly. All right, so the square is usually the most common shape that we're asked to use, but we do see some other shapes come up from time to time. And so it's helpful to think about those formulas ahead of time. So for a square, our area is, of course, side squared. Semicircles sometimes come up. That's going to be a half circle, pi r squared over 2. The equilateral triangle, this is a formula that you probably did not learn in geometry, but I'm going to give it to you here. We can talk later about why this formula is what it is if you want to see a proof of that. But square root of 3 over 4 s squared. It involves using those 30, 60, 90 triangles and the area of a triangle formula, which you do know, 1/2 base times height. An isosceles right triangle, that formula is just going to be 1/2 side squared because it is just half of a square, an isosceles right triangle is. And your hypotenuse, which sometimes you may need that length, would be s times the square root of 2. Again, going back to special right triangles. All right, so let's look at an example with each of these. We're going to use this same region. We can use our same representative rectangle here, but the difference is that it's going to become a different part of the shape. Depending on what shape we're talking about, this is going to be a different part of that. So let's go back to back here, and I'm going to switch to equilateral triangles. Let me take it back. Oh, it looks like I need to turn off the square. It's doing both of them. So let's just do a few. So you can see, as I drag it across, again, just like with the squares, we start out with small triangles. The triangles get bigger, and then as we get closer to the edge, they get smaller. And if I fill in the number of triangles, then you can see the shape there. Similar to what it looked like with the square, but obviously a little bit different because, we're not coming straight up and going straight across, but it's making more of that point that a triangle makes. I'm going to turn it back that way as we leave it. So with our equilateral triangles, the rectangle that's in the region is a side of the triangle. Let me write our formula down here, square root of 3 over 4 times side squared. So that side, again, is top minus bottom, square root of x minus x squared. And that's the only variable that I have in my formula for the area of the shape. And so I'm ready to plug into the integral. I'm going to integrate from 0 to 1 again. Square root of 3 over 4 times the side squared. And then, of course, times the height of the prism. I'm going to skip save semicircle for last. Let's jump over here and do the isosceles right triangle, which is not on our isosceles right triangle is not one of the choices that I can show you what the shape would look like, but we can go ahead and find the volume of the shape. My area formula is 1/2 side squared. The representative rectangle in the region is still the side, which is going to be top minus bottom, square root of x minus x squared. And so I can plug that into the formula for volume. We're going to integrate from 0 to 1, 1/2 times the side squared times the height, which is dx. All right, finally, let's look at the semicircle. And I will go back and show us what that would look like. Let's turn off the triangles. Let me make this lower. And let's put in a semicircle. So here's what our shape looks like with semicircles. And what's really important to notice here is that the representative rectangle, which we've drawn in our region, this vertical line, which we're seeing here on the screen, notice over here on the semicircle that it is the diameter of the circle. Again, that representative rectangle that we're drawing in the region is actually the diameter of the circle. Now let me stretch those circles out, semicircles out, make it more of a solid. And there you go. You can kind of see what that solid would look like. But again, like I said with solids of revolution, we don't have to be able to picture this as long as we can figure out what this representative rectangle is in terms of the shape that's our cross sections for the solid. In this case, this representative rectangle let me go back and write the area formula. Area pi r squared over 2. My representative rectangle here is actually the diameter of the semicircle. Top minus bottom, square root of x minus x squared. That's now the diameter. But I need a radius, and so of course the radius would be the same length divided by 2. And that's the only variable that we need for our formula. So we can plug in and find the volume of this solid from 0 to 1. We're going to do the area of the shape, which is going to be pi over 2 times my radius squared. And in this case, my radius is square root of x minus x squared over 2 squared dx. That one tends to be the most challenging because it feels like we're kind of doing the solid of revolution and we just want to do pi r squared, but that is not what this is. These are semicircles coming up out of the paper. And so we're doing pi r squared divided by 2, keeping in mind that that rectangle we drew in the region is actually a diameter and not the radius, which is what we had what it would be if we were rotating around an axis. All right, one final example. Find the volume of the solid whose base is bounded by x cubed, which we've already got a graph for, y equals 0, which is the x-axis, and x equals 2. So I'm going to draw in x equals 2. This is our region. Cross sections, we want to take perpendicular to the y-axis, and those cross sections are squares. So this time, we're going perpendicular to the y-axis. I'm going to draw in my representative rectangle. This time it's going horizontally, which means that my integral, whenever we're ready to write it, is going to be a dy integral. Formula is still the same, area of the shape. My area is side squared. But in this case, since I'm going horizontally, side is going to be equal to right minus left. And remember, when we're integrating with respect to y, my equations need to be in terms of y. Right now I have y equals x cubed, which is in terms of x. But if I solve that for x, x would be equal to the cube root of y. And so that's the version of the equation that we need to use so that it's in terms of y. So let's figure out what right minus left is here. If I look at my rectangle, on the right is this vertical line, x equals 2, minus the left. The left is that cubic function, which we solved for x, and we got the cube root of y. So this is going to be a side of the square. The squares are going to come up out of the paper, but this is one side of the square. And so I'm going to integrate the area of the shape, which is side squared, 2 minus cube root of y squared dy times the height of the prism, which is dy. We need limits on our integral. Remember that since we are integrating with respect to y, these need to be y numbers. And so I'm going to look at my graph. My lowest value of y is, of course, 0, the x-axis. And then we're going all the way up here to this point where x equals 2 and y equals x cubed intersect, which is, of course, at 8. That's our highest y value. And that would give us the volume of that shape.